So let me start with the state of the fusion industry as of May 2026. I'll just read some of these off. So first thing is total investment in commercial fusion is very good. It's over $10 billion, just slightly. There's 53 companies that are developing commercial fusion systems. Uh, Out of that group, there's 8 companies that are part of the U.S. Department of Energy pilot plant fusion development program. Those are CFS, Tokamak Energy, Zap Energy, Exemer Energy, Type 1 Energy, Focused Energy, Realta Fusion, and Thea Energy. Now, out of those companies, there's also 4 companies that have negotiated power agreements. They include CFS, Helion, Proxima, and Type 1 Energy. Each of those has multiple negotiated power agreements with power companies. Now, the one place where we have room to grow yet is commercial companies with machines achieving Q greater than 1. Today, there's nobody that's done that. Obviously, the only company that has done it, the only lab that has done that so far, is the National Ignition Facility. But hopefully, this year will change that, and we'll see some commercial companies increase and join that number. Next. Okay, so just to put fusion compared to comparable industries. So, as we said earlier, we have about $10 billion in investment. To put it in comparison, VC investments in solar power have reached about $231 billion. That's billion, not million. So about 23x what fusion is achieved today. Of course, it's a slightly older industry, so that's part of it. Another comparison, if you look at the companies that are doing AI startups, the big two are OpenAI and Anthropic. Together, they have raised $194 billion. Again, with a B, not with an M. Well, it's a little more comparable. EV startups in 2021 alone had $19 billion in investments. VC investments in battery energy storage system markets in 24 alone, in 1924 alone, was $16 billion. And investments in Rivian, that's a single company, that's an EV company, prior to its IPO was about $10.5 billion. So as we go through this, I want you everybody to think about what does the commercial fusion market need to do to get similar investments. And with that, let's go ahead and turn it over to our first presentation. Thank you, Frankie.
All right, our first presentation is going to be from Mike Dunne, co-founder and CTO at Inertia.
Hello, my name is Mike Dunne. I'm a co-founder of Inertia Enterprises along with Jeff Lawson and Dr. Annie Croucher. I serve as the CTO. I'm responsible for the design and delivery of the fusion pilot plant and all of the technologies that fit within it. Now, together, we founded Inertia because of a monumental breakthrough in fusion science. Of the many dozens of approaches to fusion that have been explored over the decades, it turns out only one approach has been proven to get to that point of net fusion energy gain. And Inertia has the exclusive rights to take forward key intellectual property to take that technology to market. This is why we see ourselves as the commercial fusion company, no longer searching for elusive physics, but rather with a focus on harnessing technology, building a supply chain, and taking that to market. Now, this approach has attracted very substantial investment from our partners. I'm really happy to recognize Bessemer Venture Partners as the lead, with Google Ventures and many others you can see on the slide here that are taking us forward over these next few years in order to get to that point where we can build, turn on the fusion pilot plant. This has all been enabled by a breakthrough that was achieved on the National Ignition Facility at the Lawrence Livermore National Lab in California. But I can tell you, getting there was not easy. It took perhaps 5 generations of high-power laser systems. It took classified codes and data, even to establish the right regime in which fusion ignition could occur. And then, after the NIF turned on, it was over 10 years of experimental tuning to reach that point of ignition, to get to fusion burn, to get to energy gain. And I'm really proud that it was my co-founder, Annie Croucher, and the wider team at Lawrence Livermore National Lab that reached that point in December of 2022. And since then, those results have been repeated many times. The gain has increased yet again and again. And perhaps this time last year, got to the point of a gain of over 4, which is what's called Q scientific. This is measuring fusion energy output compared to laser energy delivered. The other thing that was learned over this past 10 years or so is that even small changes in the configuration of the laser or the target or how they're combined together, even small changes which the codes say should all be fine, can lead to devastating loss of gain, can lead to essentially quenching of the fusion burn in ways that are simply not understood. And so there is a very narrow window of operation that has been validated by the NIF. And we should be respectful, I think, of what we've learned over that period. There's been a real salutary lesson for all of us. Perhaps history showing us time and again, speaking as a plasma physicist, that plasma physics is hard. It's an unpredictable and perhaps unforgiving science. And this is why the breakthrough by Annie and her team is such a game changer. And so Inertia strategy is then quite simple. It's to stick as closely as possible to that proven window of science, and then take the most direct path, the lowest risk path from there, to integrated operation of a fusion pilot plant and to commercial fusion deployment. Version 1 of the plant, the pilot plant itself, perhaps will not be the most beautiful of pilot plants, certainly not the most optimized. It's there to teach us how an integrated plant can work. I've spent my career, most of it, designing, building, and operating large-scale, complex research facilities. Each time, as we turn them on, there are complexities, there are surprises in their integrated operation. And we've all seen this journey in our everyday lives, as how advanced technologies are deployed into the market. Everything from mobile phones that started off as bulky briefcase-sized devices, and are now these beautiful, sleek works of art that we carry around, and then maybe all the way over to rocket science. The first version of the Raptor rocket that sits in the SpaceX Starship. Version 1 was a complete mess of flanges and welds, actually by design, so the team could learn. Sometimes it would blow up, sometimes it wouldn't work appropriately, so they could reconfigure. And that taught how to progress through version 2 to version 3, which is now an additively manufactured, beautiful, sleek system, that works, and powers that Starship. Similarly, we need to respect the complexity of the fusion pilot plant and not pretend we can optimize it too early. We need to be able to learn and learn at full scale. We need to be able to design in margin and flexibility to enable that learning, to allow us to respond to the unknown unknowns, and provide a pathway to continuous improvement, optimization, using data from that full-scale system. And so our approach at Inertia is to build in 4 technology pillars as we piece together this pilot plant. The first is at the heart of why Inertia exists at all. It's the performance of the fuel target itself, using that only known approach to fusion physics that produces energy gain, and staying as closely as possible to that window of operation that the NIF has taught us. Now, fortunately, when we take a look at the integrated system level of our plant, we only need relatively moderate gain, somewhere between 15 and 20, in order to get to net power output to close the fuel cycle to get to that first plant. And then just a factor 2 more than that, a bit less, perhaps a gain of 35 or so, will get us to a gigawatt worth of electricity onto the grid. The second pillar is how we manufacture the fuel that provides that performance. We need to scale up from these lovingly crafted individual R&D prototypes, that take hours and days to make, to mass manufacture production lines that maintain acceptable tolerances, such as the roundness, the roughness, the placement of the fuel, and so forth. If we can do that, then we can amortize the cost of these large-scale manufacturing processes across millions, actually hundreds of millions of targets per year, and so bring their unit cost down to around $1 or so a piece. The heart of the system is, of course, the high-power, high-energy laser. The NIF has taught us what the output of that laser needs to look like in terms of its pulse shape, where the energy goes, its bandwidth, and so forth. But the technology of the NIF was designed to be an R&D device, not a power plant. And so we need a change in technology for our system. And actually, it's a similar transition to what has happened in almost every other part of our lives across society, a transition from vacuum tubes to semiconductors. In our case, flash lamps that power the laser to semiconductor laser diodes. And we need to scale up that market of these currently boutique laser diodes, scale up the market by a factor of hundreds, maybe a factor of 1,000 or so. This will bring the cost down to an affordable level. And these laser diodes provide inherently the efficiency we need for a power plant, going from a wall plug efficiency of about 1% or so on the NIF to 10 to 20% using these semiconductors. They also provide inherently very high repetition rate, going from 1 pulse every hour or so to many, many pulses per second because of their inherent efficiency. And very importantly, they also provide us with a compact form factor that allows us to build these lasers in a factory, wherever it may be, and then truck ship the lasers to the plant. This modular approach provides us with a lot of flexibility, a lot of adaptability. It also is the approach to get to high availability of the plant, high maintainability, which you need for the type of base load electricity supply that fusion will be pointed towards. Now, of course, we know there will be surprises. There will be non-idealities in the fuel manufacturer. Our codes say that a factor 2 or 3 increase in the laser energy from the NIF should be sufficient. But I guess our approach at Inertia is if you're going to build a big laser, you might as well build a really big laser. And so we adapt another factor of 2 margin on top, a factor of 5 overall to get 10 megajoules for our laser system so that we have real robustness, real margin for these unknown unknowns. And then finally, put this together in the integrated plant itself. And here again, our approach is to be as modular as possible, so we can learn as we go in the areas that require the integrated plant to teach us, whether it be breeding and recovering the tritium fuel and maintaining its inventory at an acceptable level, or whether it be the heart of the system, the chamber that holds the fusion system. We don't have a material that can last forever. And so we adapt and develop a system that can be replaced periodically, a line replaceable unit all the way down to the chamber of the fusion pilot plant, and then protect that chamber wall with gas to let us use a simple conventional steel that provides us with a very direct path to market. Now, all of this, of course, is enabled by a very substantial suite of public and private partnerships. Inertia is funding perhaps the largest ever privately funded public-private partnership across the DOE complex, based at the Lawrence Livermore National Lab. And we also have partnerships across the vendor base, whether that be with the semiconductor companies, optics, lasers, large-scale energy manufacturing companies, and so forth. Perhaps the most important aspect of these partnerships is to build the vendor base, build the supply chain, everything from the laser glass to the optics to those fuel targets, of course, the semiconductors that lie at the heart of the laser, all the way through to the steelwork that makes up the plant itself. And what we've seen, even in these first few months of Inertia's operation, is the growth and engagement of that vendor base. You can see in this chart on the right, the map, the vendors that we've been partnering with just in the first 3 months of operation, forming and driving in how we can scale up not only to that first pilot plant, but scale up to the rollout of the fleet afterwards, because our eye is always on that commercial deployment. The pilot plant itself, perhaps its most important aspect as we sit here today is to ensure that it is deliverable. That means we have a supply chain we can go to, materials that we can procure today, and materials and systems that are affordable. We need to be able to earn the right to operate at full scale, adapt and learn as we go, and optimize from there onwards. Because of the uncertainties in any large-scale system, we build in margin in every single aspect of this, and we build in adaptability through modularity to those operational uncertainties that will tell us how to build availability, it will tell us how to build maintainability, and it will tell us how to optimize for full commercial deployment. We do not need those things on day one, just like in any other part of our technology lives. We need to be able to learn and adapt, optimize as we go. Our starting point is some work that I led over a decade ago at Livermore Lab, putting together an integrated power plant design with many, many different partners. That provided a basis for how we close the fuel cycle, getting a tritium breeding ratio much greater than 1. Of course, closing the power cycle, this is a power plant, but also do so in a way that teaches us those concepts of operations and maintenance for rollout of the commercial fleet and for the supply chain that needs to put the pieces together for that fleet. And then importantly also teaches us all, including the public at large, what a fusion pilot plant really looks and feels like, so we're comfortable having it sitting next door to us, powering our cities and our wider society. So let me wrap up and summarize, perhaps the most important point, the reason Inertia exists is because of this breakthrough, this 60-year event that took us from exploring physics to knowing the physics regime that works. To then harness that and harness it with margin and adaptability. So because we want to be able to optimize as we go. Our focus as a company is on the fuel target design and of course the manufacturing at high scale, the targets that are needed for those fuel delivery systems. The laser itself, everything from the semiconductor diodes through to the integrated system and the supply chain that underpins all of that. And every step along the way to do so in the context of a self-consistent integrated fusion pilot plant design. So this thing can operate at scale and we can learn how to optimize it from there onwards. Our approach is to take that most direct path from the proven physics of the NIF to that commercial pathway for the pilot plant and optimize by learning at full scale. So finally, let me thank the organizers of the Fusion Report for this opportunity to present Inertia to you all. I'm looking forward to the panel discussion. I hope that of the many approaches being explored, others can find a physics basis and a pathway to a commercial deployment. Really looking forward to the discussion. The world for sure needs fusion. Thank you.
Next up, we have Brian Berzin, CEO and co-founder at Thea Energy.
Hi there, I'm Brian Berzin, co-founder and CEO of Thea Energy. I'm excited to be back again this year to give you some updates on our recent progress. As a quick refresher, Thea Energy is a spin-out of the legendary Princeton Plasma Physics Lab at Princeton University. PPPL is one of the birthplaces of fusion research in the world, and actually was the place where the stellarator, our flavor of fusion technology, was first invented. That was about 70 years ago. Those 70 years were critical for the scientific research and development that was required for private startups to think about commercializing a technology. So over those 70 years, government-funded research, academic research pushed forward the stellarator from the theoretical basis actually through to the completion of large-scale integrated devices that ultimately showed a high triple product, high fusion conditions being achieved. And also they gave us codes and computational tools that were benchmarked against real system performance that allow us to optimize and engineer better stellarators and better power plants based on these scientific foundations than ever before. The stellarator has always had some just really important advantages for the commercialization of fusion energy, and those are related to its steady state nature and its low recirculating energy. That's really what a power plant needs to be, a device that works continually and that puts a lot of energy onto the grid rather than having a tremendous amount of energy needing to be recirculated into the device to power a pulse or a laser or a center solenoid. However, there's always a however for fusion. The precision and complexity of making that three-dimensional kind of French crawler-shaped configuration of the stellarator has always been very limiting. Most stellarators that have been built and operated across this world went significantly behind schedule and over budget. And that is unacceptable for the commercialization of a technology. And so this is a picture of W7X, the large-scale integrated stellarator in Germany. And yeah, it's a feat of science, it's a feat of engineering, but it really showed this Achilles heel for the stellarator. The superconducting magnets that are required by these traditional three-dimensional modular coil stellarators, they're massive, massive pieces of hardware that require precision on the level of a millimeter. And that precision, no matter whether it's fusion or aerospace or other types of hardware, precision and complexity in hardware are just incredibly costly and incredibly time-consuming. That device was 10 years behind schedule and went 3x over budget. If you're building a power plant and you deliver it 10 years behind schedule and 3x over budget, you're not selling many more power plants after that. The reason why we decided to found Thea Energy and spin this out of Princeton Plasma Physics Lab about 3.5 years ago was because we applied what is actually a fairly well-known type of control system called a phased array to fusion for the first time. Phased array control systems are how radar systems and cell phone towers and GPS satellites work, and allows us to use much smaller discretized hardware, and on the back end with a software stack, individually tune independent variables. So to be clear, we have not eliminated any precision or complexity. We've just transferred quite a bit of it out of hardware and onto the software stack, onto the control system. And that's where we have almost like software-like scalability. We've built the control system. We only need that control system. It's the same control system for every single magnet in the array. That allows us to actually take a bunch of hardware, some of which have defects or wear and tear, or were potentially mismounted. And we talked about this a bit last year. Allows us to take all that hardware, even though things might not be perfect, and to tune them into perfection using software. That was the game changer for us. From there, over the past 2 years, and even more recently since the last webinar, we've continued to get really good at scaling the manufacturing of our core magnets. The magnets that we utilize, there are about 300 of them, and they're all the same. And they are mass-produced. They are mass-produced via manufacturing technologies that are pieces of metal that are stamped and forged in the winds of the superconducting magnets. They can be done in tension, all in one plane, around a bobbin. The Lego block of a superconducting magnet is called a pancake. We can mass-produce these pancakes and then stack them to the appropriate magnetic field spec magnet, all on the same manufacturing line. And these are manufacturing lines. You can probably see the very small video window behind me. Now, this is a manufacturing line that really resembles an automotive plant, not needing 3D printing, additive manufacturing, extreme precision. This is something that truly scales. And we've actually now built these full-size integrated magnets. And from here, over the next couple of years, we're really focused on scaling the production. So we can make one magnet every week or two in this very small manufacturing facility behind me. We're about to take a second manufacturing facility about a mile down the road here in New Jersey, where we will scale a manufacturing line to produce one magnet a day and more. That is ultimately how we can build many power plants across this world via high throughput manufacturing that really resembles every other industry out there, not super techy, difficult to manufacture fusion. Well, we probably can't go a day without hearing about AI, so I wanted to spend a couple minutes here talking about how we utilize AI at Thea Energy and how it's being utilized across the industry. So across the industry, no matter what architecture, AI via surrogate models is utilized to look at much larger design universes of solutions. And then when we have a solution set that's viable, to take it and push it through a parametrically derived engineering workflow to build a digital twin that resembles the devices that we want to build. Quite uniquely, at Thea Energy, we also can leverage AI for our control systems, for the software stack that runs, for us, 324 independent variables. And that is a game changer for the Stellarator. Most all Stellarators to date are based around one design point and based around what humanity knows at that point in time when it was designed. That means that those devices can't take advantage of future breakthroughs, and there are continually better performance or even breakthroughs being made. One that comes to mind is turbulence modeling and suppression. The world will get better at those things 5, 10, 20 years out. And if your architecture is designed only for one operating point, it means you'll never be able to take advantage of those learnings. It will just have to go into the second generation. That's as good as the device will ever be. Because of our unique ability to have an independent control system in an array of magnets, we can actually, via software level update, take advantage of those higher performance modes in the future. That means a power plant built today can be a better power plant in 10 and 20 years. And that's an important thing because power plants work for decades and decades on end. So you want to make sure that these devices have high uptime, high capacity factors, and low maintenance, and have high performance for their uptime. So this is very unique to us. and allows us to, again, have the software level update to have higher performance even in the future. Speaking of power plants, a major milestone that Thea Energy accomplished just earlier this year in Q1 was the successful completion and certification of a milestone for the pre-conceptual design review of our power plant architecture. This is part of the Department of Energy's milestone-based fusion development program that we and 7 other awardees are a part of. And this milestone focuses on a power plant. The design milestone spanned the physics basis into a closing of an engineering architecture through the techno-economics, capacity factor, maintenance cycle requirements for the entire system. So this is what is the most cohesive look of a fusion power plant architecture to date across the industry, and one that really, why the milestone program was set up, enables us and our peers upon their completion of the milestone to really pursue putting fusion power plants on the grid in a structured, thoughtful way that can be further enabled by this government public-private partnership and cost share. What I want to highlight real quickly here as we go into the video is what you're about to see on the screen. These are the same subsystems that are utilized by other types of power generation systems that are online on the grid today, including combined cycle natural gas and nuclear fission. These are the same balance of plant technologies that have been built 1,000 times over around the globe and work at a very high, high capacity factor, high reliability that we want for fusion energy. We do not like first-of-a-kind technologies here, actually. We like that proven, resilient, massive manufacturing supply chain and high reliability architecture for the balance of plant that we can utilize and actually now work with commercial partners to deploy integrated systems. So this is a top-down view of our Helios power plant. Our Helios power plant is about a 400 megawatt device, and we'll dive in on the energy balance here in a second. This is a fairly traditional plot of land. It's about 40 acres. The fusion architecture that we've developed, Helios, doesn't need too many site-specific requirements. And as I pull up the second image here that expands upon the various subsystems, a lot of these subsystems are those same traditional energy generation subsystems that you see on those other types of power technologies online across the grid today. We are getting very good at the stellarator hull, using our planar coil architecture to reinvent the stellarator to create a cheaper, more manufacturable, more scalable stellarator fusion island. But from there, when you take the energy out and thermalize it, boil some water, turn a turbine, and generate electricity, those balance of plant technologies are fairly traditional and utilized by those other forms of power generation. So one subject that we spent a little bit of time actually last year talking about, but also that I highlighted at the beginning of the call, talking about the advantages and the disadvantages of the stellarator. One long-standing advantage of the stellarator was its low recirculating energy requirements. This actually can be shown on the bottom of the Sankey diagram. You can see this very small purple line with a label of ECRH. That's 1 megawatt of gyrotron heating that goes into the plasma, largely to dispel impurities from the core. That is the recirculating energy required for plasma heating in this architecture. Largely in this operational mode, the plasma is heated by alpha particles. It is ignited. And that advantage allows us to take the energy that gets converted into electricity and use it to be put on the grid to make power. There are other house loads. You can see them come off of the total generated electric and gross electric lines. Those are our house loads for pumping and cryogenic systems and other balance of plant systems. But largely, the electricity that gets generated is used to make power on the grid, not recirculated. And most other fusion architectures, unfortunately, have to recirculate a tremendous amount of that electricity created back to power another pulse. And that ultimately just directly impacts the bottom line of your power plant architecture. If you're making the same size balance of plant and fusion system, but the amount of electricity you have to recirculate is half of the electric energy created, your economics are going to be half as good. So a major advantage of the stellarator is that for its footprint, for its power generation on a thermal and electric amount, it is probably the most efficient energy and therefore efficient use of capital for a power plant architecture. A couple of other interesting things that I wanted to talk about today that are part of the design review and part of the paper that we recently released to archive relate to the practicality of our power plant architecture. One of them is actually just related to how you get the exhaust out of a plasma. Our stellarator architecture, similar to other stellarators or tokamaks, require a diverter, pretty much an exhaust manifold for the fusion plasma to function in a commercial environment. Historically, stellarators use island diverters or other diverters that have a three-dimensional component to them, which are just pretty unwieldy to build and also don't necessarily work the best when they even work compared to tokamak diverters. We have successfully utilized, and we'll have a peer-reviewed paper on this coming up, utilized an X-point diverter. X-point diverters are what have been developed really over the span of 30 to 40 years for tokamaks and what are being utilized in ITER as well as other industry-leading devices. We now can take those lessons learned, those technologies developed, and directly utilize them to implement a stellarator X-point diverter. Not only is that just a massive simplification of the engineering required for a stellarator diverter of any power plant, this also allows us to just have a higher performance system. X-point diverters are about 10 times better at pumping out gases than traditional island diverters utilized by other stellarators. So this is one fundamental requirement for the commercialization of a stellarator that we've now enabled here. Another one is actually just a maintenance scheme. I'd say, just a maintenance scheme. It's pretty fundamentally important to any fusion system architecture that there's a way to manufacture the components and then bolt it together on site, and then also have a systematic, repeatable, reliable maintenance scheme to replace parts when they're worn down. For instance, the first wall, any fusion system's first wall has a finite lifetime that will require periodic replacement. But also just over a power plant architecture's life, you're going to have parts of the system have wear and tear and need replacement. We now have a limited amount of parts in terms of the cryostat, which you can see on the screen. 12 sections of the cryostat and vacuum systems are all the same. And from there, we can remove fairly traditionally manufactured support systems. You can see those things that look like erector sets on the left-hand side. Those are structural supports, and we make them out of pieces of stainless and other types of steels that can be welded together. No additive manufacturing, no in-depth, expensive manufacturing processes required there. And then the way that we assemble and replace and maintain other parts of the system can be done with a low unique part count and also via very systematic replacement cycles that resemble us kind of peeling back layers of an onion to replace those components over the lifetime of a power plant architecture. We're excited to share more about this power plant architecture coming up via peer review and continuing to build the team and technology required to deploy and scale fusion across the world. So thanks for the time today.
Thank you, Brian. Next up, we're going to hear from Charlie Baynes-Reid, CFO and General Counsel at Type 1 Energy.
Hello, my name's Charlie Baynes-Reid. I'm the General Counsel and CFO for Type 1 Energy. I'd like to thank our colleagues at Fusion Report for inviting me to speak to you today with respect to the 9-year shot clock. My background, I'm a corporate finance lawyer by training, spent a number of years in the UK, Japan and Australia where I joined Macquarie Capital with a focus on energy and infrastructure. And after spending 10 years with Macquarie and then pursuing some independent transactions, I was first introduced to Fusion about 5 years ago when I met Chris Mowry, our CEO, and was subsequently offered the chance to join Type 1 Energy after Breakthrough Energy and Chris made the initial investment in 2023 in the company. Type 1 Energy is a magnetic confinement stellarator OEM, so we are designing and building first-of-a-kind stellarator-based power plant for commercial level baseload power generation. And importantly, we have an end customer already in the form of TVA, who has been a significant partner and with whom we are developing a first-of-a-kind power plant project at Bull Run, which is a decommissioned 900 megawatt electric coal-fired power plant in Tennessee. And relevant for the purposes of this conversation, the intention is to break ground on that plant around the end of 2028 and have electrons on the grid by 2034, which is consistent with the 9-year shot clock that we're all here to discuss. So as I'm sure everyone is more than aware, the significant increase in baseload energy demand and electricity demand, coupled with decarbonisation goals, requires significant expansion with respect to reliable carbon-free baseload energy. With respect to that, much of the focus has been on SMRs, but increasingly people are aware that fusion is far closer to commercialisation than was previously considered to be the case. And particularly with stellarators that we are developing and the core technology for our offering, stellarators offer you a unique opportunity to create baseload power generation with fusion, which operates in a stable and steady state environment, by which we mean once you turn the machine on and create the fusion conditions sufficient for ignition, if you continue to provide the necessary fuel, deuterium, tritium in our case, then the machine continues to operate in a stable and steady state. That lends itself significantly to what is an increasing gap in baseload power generation capacity, driven not least by general electrification trends, as well as onshoring of manufacturing, certainly in the US, as well as data center proliferation on a global scale. So fusion, why is fusion so exciting? It's been talked about for a number of years. This really is the ultimate goal from a sustainability perspective, because fusion is safe, clean, and abundant. So sustainable power for the entire planet for millions of years. It's a virtually limitless and safe fuel supply. There are no weaponizable materials involved. It is genuine zero carbon emissions, so no air pollution, and there is no long-term radioactive waste created as part of the fusion reaction. It therefore can provide consistent baseload power. And importantly, in the last 3 years, one of the things which has encouraged investment in fusion was the codification of regulation, particularly first in the UK and more recently in the US, which gives certainty to the regulatory framework, so much so that in the US, the NRC has in fact delegated the authority to license and permit fusion power plants to a number of the signatory states. Ultimately, as a result of the nature of the technology as well as the streamlined regulatory pathway, there is a demonstrable path to competitively priced electricity, which is the ultimate goal. So we are highly confident that by nth of a kind plants, we can achieve an LCOE of $50 per megawatt hour or less, so commensurate with coal. In terms of why fusion is exciting and should be so exciting for everyone, the reality is, given the statistics with respect to total baseload demand in the next 20 or so years, all forms of power generation are going to be relevant, but increasingly fusion, as it proves itself to be commercially viable, will take an increasingly large share of that market. It has characteristics with respect to baseload capacity and zero emissions, which are highly appealing. It's extremely cost effective at nth of a kind. It's efficient both from a materials and a land use perspective. The fuel supply is abundant. There is no long-term radioactive waste, no weaponizable materials, and no risk of nuclear accident. So highly appealing from a social license perspective as well. And as demonstrated by the proposed project at Bull Run, it's also capable of repurposing existing infrastructure, which is highly appealing, particularly in an environment where coal and other fossil fuel powered plants are being taken offline. Now, in terms of the stellarator, one of the interesting things about fusion, there are multiple approaches to potential commercial fusion. One of the most well understood is magnetic confinement, and in that realm, there are two key technologies, the tokamak and the stellarator. The tokamak has been the workhorse of fusion and experiment and scientific advances for the last 50 plus years, and has been the workhorse from an R&D perspective. Now, the stellarator, a close cousin of the tokamak, is a tokamak with a twist. The important thing that achieves is it allows you to mitigate the need to pulse electricity through the plasma, and mitigates therefore the concerns with respect to instability and disruption, as well as the need for significant recirculated power in order to maintain the reaction. The stellarator, as mentioned, operates stable and steady state, but doing so, in order to achieve that, you need to create a very specific configuration of technical magnets which are non-planar, so very specific geometries in a very specific configuration, and the optimization of those geometries and those magnet configurations in order to maximize the efficiency of the plasma confinement has been one of the key challenges, which until recently was seen as a barrier to stellarators being broadly adopted in the context of commercial baseload power generation. Now, importantly, in the last 5 years, the maturity of HTS cable technologies, the scaling of exascale computing capacity, and the development of other enabling technologies, including precision manufacturing and 3D printing, have allowed stellarators to push forward in a way that was previously not seen as practical or scalable, to the point that we now have a high degree of confidence that we can take the fundamental architecture, which was demonstrated most recently by the W7X program at the Max Planck Institute in Germany, and create a highly optimized and therefore economically viable stellarator for baseload power generation. Type 1 was effectively a company specifically designed with the shortest path to the commercialization in mind. In order to achieve that, Breakthrough Energy and Chris spent a significant period of time studying the entire fusion landscape, identifying the world's leaders in terms of stellarators who had built all of the modern stellarators in the world today, including the HSX machine at University of Wisconsin-Madison, as well as Thomas Pedersen, our CTO, who was one of the co-directors of the W7X program at the Max Planck Institute for more than a decade. So between Thomas, David Anderson, Chris Hegner, and John Canick, we have some of the leading minds with respect to stellarators, both from an academic standpoint as well as practical experience in building these machines, albeit using low temperature superconducting magnet technologies, and being able to rely on the learnings from those processes is core to everything we do in developing a practical and feasible path to commercial power generation using stellarator technology. Importantly, in order to achieve that preeminent technical team has been complemented by a very experienced management team with experience owning, operating, and commissioning technologies and power plants all over the world, and being able to therefore implement the execution discipline required to achieve what is a very ambitious timeline for commercialization. As mentioned, our technical leadership includes John Canick and Thomas Pedersen, our Chief Science Officer and Chief Technology Officers, respectively. With respect to the leadership team, Chris Mowry, our CEO, spent his entire career in energy, was in fact a founder of one of the first SMR companies. Ryan Guerrero, our Chief Operating Officer, has undertaken complex programs and managed those for the likes of Boeing and Northrop Grumman for decades. Anthony Harbridge, our Chief Commercial Officer, has spent decades with BP, with a particular focus on renewability and sustainability efforts. So this is a fantastic team with deep experience, complemented by a board of directors with significant experience, including Bill Nadir, our board chair, who has been intimately involved with a number of the national labs, and then Dan Button and Phil LaRochelle on behalf of Breakthrough Energy Ventures, and Neil Subin, who's been one of the preeminent investors in sustainable technologies, including fusion companies, for a significant period of time. So one of the key things that differentiates us, and hopefully a key validation of the credibility that this team has and our ability to execute on our ambitious timeline, is demonstrated by the LOI that was signed and announced in September last year. Prior to that, we had been working for a significant period of time with TVA. TVA is the largest public utility in the US, a nuclear utility for a number of decades. And that team signed the LOI with a view to building two things at Bull Run. The first will be Infinity One. That is our prototype machine. It's a prototype in the sense not that it needs to prove the fundamental science of the stellarator technology. That has been proven with machines including W7X. More importantly, Infinity One will be used as an engineering test bed to verify by test certain key aspects of our power plant design and configuration. That will then lead to commissioning of the Infinity 2, which will be the first of a kind power plant, a nominal 400 megawatt electric power plant, which will be built at the same site at Bull Run, which, as mentioned, was previously a 900 megawatt electric coal-fired plant. So we're able to repurpose that existing infrastructure and interconnectivity and grid connection for the purposes of developing that first of a kind plant and bringing electrons to the grid by 2034. So much of what we do with TVA informs many of the key decisions that we make with respect to design and engineering parameters. In addition, we're working very closely with a number of other partners, including AECOM and Westinghouse on the engineering and design side, all of which informs the capacity factors and parameters for our first of a kind power plant. So Infinity 2 is intended to be a minimum 400 megawatt electric power plant. And importantly, we've worked with consultants and AECOM and others to ensure that we can deliver not only a first of a kind plant that is competitive for first of a kind technologies in the power generation setting, but more importantly, we can demonstrate a very credible path to nth of a kind economics, which will be able to deliver an overnight cost and a competitive LCOE, which will be competitive with coal and combined cycle gas. One of the things that we like about the OEM model is our ability to scale. So we do not intend to own and operate. We intend to partner with the likes of TVA, who are experienced utilities and end customers, who will ultimately operate these plants on a go-forward basis. That has a number of advantages for us, including capital efficiency, but importantly as well, as we look to help to drive the maturation of the supply chain, which needs to mature in parallel with our core technologies, it's important to demonstrate to those supply chain partners that we will have a pipeline of opportunities within a relatively short period of time, which will then encourage the investment required for the supply chain to scale to our needs. In addition, we see fusion as a global opportunity, and therefore we partner with groups across the globe, including Australia and the Gulf and Europe, to not only develop the supply chains and the potential partnerships and similar projects to the Infinity 2 project with TVA, and part of that will be achieved through the Infinity Fusion Consortium, which was stood up following the signing of the LOI last year and already has several additional utility signatories, and we continue to negotiate with other fast followers with a view to being able to execute multiple projects relatively contemporaneously, given that we are not constrained by being an owner and operator of plants. It also means that our business model allows us to start generating revenues far sooner. We have already started generating revenues from some limited POs from TVA with respect to engineering services required to facilitate the Infinity 1 and Infinity 2 projects. But importantly, when we sign that first of a kind contract in 2028, that will be a meaningful revenue event for us. And our OEM model will allow us to sell that technology and license it to our end customers, and then provide an annuity revenue stream through support, engineering, and maintenance services for the life of the plants. So there we are. It's an exciting project. It's ambitious, but we feel, given what has been achieved to date by our technical leaders with projects such as W7X and HSX at the University of Wisconsin-Madison, we have a very credible and tangible pathway with a series of clearly defined technology milestones which allow us to de-risk our technology on a path to breaking ground on a first-of-a-kind power plant in 2028 and putting electrons on the grid in Tennessee by 2034. So with that, I'd like to thank you all for your time today. We look forward to seeing many of you as we continue to develop this exciting project.
Thank you, Charlie. Next up, we're going to hear from Derek Sutherland, Vice President of R&D from Realta Fusion.
Hi everyone, I'm Derek Sutherland. I'm the VP of R&D at Realta Fusion. We are a startup fusion energy company located in Madison, Wisconsin, developing axisymmetric magnetic mirrors. So we'll start off with a company update as far as our investments to date and where we're going next. So we've raised between around $60 million of investment to date with our latest equity financing as a $36 million Series A in May of 2025 led by Future Ventures. We're currently operating a device called WAM, which I'll show in the next few slides, and we're using those data to validate our real twin simulation codes that are being used to design our next scale-up devices that we're targeting first plasma in 2028 to 2029. Our roadmap is towards deploying the first-of-a-kind fusion power plants in the 2030s. So magnetic mirrors, as a basic concept, is a form of magnetic confinement fusion. And I like to start with one of the simplest approaches to fusion, which is a straight tube full of magnetic fields that you're using to confine a hot fusion plasma. You basically make this with external coils wrapping around the outside of a cylindrical pipe, and those field lines constrain the motion of those particles perpendicular to the magnetic field, but it does not constrain it parallel to it. The drawback of this approach, where it's just a straight pipe with no gradient in the magnetic field, is that the device would have to be quite long, on the order of 100 kilometers, to actually allow for achieving the fusion temperatures in the core of the plasma. And so effectively, some method of plugging the ends of this tube is required. And that's where the mirror force comes into play. So the basic physics principle behind the magnetic mirror is that you are creating a gradient in the magnetic field with external magnets, which in our case are high temperature superconducting coils. This gradient in the magnetic field applies a force to these charged particles because each of them are basically baby magnetic moments that are causing the particles to bounce back and forth between the mirror turning points. And so because these particles bounce back and forth down the length of this pipe, it's reflecting between the two turning points, hence why the mirror gets its name. Though this is a very effective way of plugging the ends of the device and making sure that it stays much more compact, it's not a perfect confinement system, and some of those high energy particles leak out the end. And so we basically need to make sure that the confinement is good enough for getting to net gain, but it's never going to be perfect, nor do we want it to be perfect. So some of the key selling points of magnetic mirrors is that they are continuously operating systems using those external superconducting coils to provide the magnetic fields for confinement, but also that there's no appreciable amounts of plasma currents. What that means is that there's no big disruption risk, which is one of the main outstanding physics risks of plasma current carrying devices like tokamaks. But besides those two features, which are shared with stellarator devices, our differences are quite stark compared to those other bigger machines. One is that cylindrical form factors mean that it's a much more modular and scalable system. Instead of having a toroidal-based fusion system where you have a plasma donut, you're keeping it straight, and so you're able to basically separate the device axially, do maintenance on it, and pull it back together. And you can also change the power output of the device by adding more modules to the length of the machine. And so what we think this translates into is a much more commercially attractive product that's both modular, scalable, and more maintainable. So going one tick deeper in the physics here of mirrors, as I mentioned, one of the challenges of mirrors is that even though the confinement is quite good out the ends, and you can improve that by going to higher magnetic field strengths, there's still a loss cone present where you have very energetic particles that still stream out the ends. We rely on this physics to actually exhaust the helium that's produced from fusion to keep the plasmas clean, but we have to make sure that the losses aren't so large that they end up precluding a high gain scenario. And so the lost cone physics basically means that going to high mirror ratio, where the mirror ratio is the maximum magnetic field you apply with those HTS magnets relative to the minimum magnetic field in the center of the chamber. As you go to higher and higher mirror ratio, the lost cones get smaller, and that means you get better and better confinement. The other big aspect of mirrors is that the double product, so that's the density times the confinement time, which is two parts of the triple product that most people are familiar with. This in tau scales as the ion energy to the 3/2 power and the log of the mirror ratio. So what that means is going to higher mirror ratio improves confinement, as we already mentioned, but also going to higher ion energy actually improves the confinement as well. This is great for fusion because fusion requires very, very high temperatures. So the physics of mirrors means that as it gets hotter, the confinement improves, and it's a positive feedback to get to those fusion conditions. This is exactly the type of physics scaling that you would want to make a fusion power plant based on it. When we look at how the Q of the mirror shakes out in terms of ion energy and log of the mirror ratio, we see that it scales basically as EI to the 1/2 power and the log of the mirror ratio again. So that tells us basically what the ion energies we need to be at in order to maximize the scientific gain, which then when you include all the other inefficiencies in the system like thermal cycles or other loss terms, that results in a net electric being high enough for net electricity production. So the takeaway from this slide is really to get to high gain in a mirror system, you need to go to high mirror ratio and ion energy, which in a way that maximizes the fusion reactivity. So the scaling law is very favorable for mirrors, and we know how to get to good enough confinement. But there's also another bit of physics that improves the confinement even further, and that's something called the ambipolar potential that arises in mirrors. And so when I talk to other people about different approaches to fusion, mirrors are often cast as a form of magnetic confinement, but truly what they are is they're a form of magnetic confinement that's being augmented and enhanced by electrostatic confinement as well. This ambipolar potential results because the ions and the electrons leave the mirror at the ends of the machine through those loss cones at different rates. The electrons go out faster than the ions. So when you're starting up one of these machines, because there's an imbalance in the charge of what's leaving the ends, you end up building up this electric potential to maintain no net electric current conditions out the ends of the machine. This is something called the Pastekov potential, and we know that the voltage of the plasma basically scales as around the electron temperature, in particular about 5.5 times the electron temperature. So what this positive electric potential does is that those electrons that would continue leaving out the ends are instead attracted back towards the confinement chamber by that big positive potential because like charges attract each other. And so what this does is it enhances confinement even more and provides pathways to a high gain design point. So all of this sounds great. You have a simpler form factor, no big risk of plasma current disruptions. Everything seems more scalable and maintainable. So what's the catch? What's the main physics risk? The main challenge of mirrors, especially axisymmetric ones that we're pursuing, is that out of the box they're interchange unstable. And so what interchange modes are is that they're a form of MHD, magnetohydrodynamic instabilities, and when these become unstable, they tend to degrade confinement quality. And so what you have to do is you have to stabilize these modes in order to achieve that really good confinement potential of a mirror. There's a couple ways of doing that. One of the legacy ways is to create these so-called minimum B configurations where you're using non-axisymmetric coils at the ends of the mirror to create a MHD stable magnetic topology. The drawback of this is that it introduces neoclassical transport, which basically means that the really good confinement prospects of a mirror when it's stable, you've now degraded it in the pursuit of making it stable. And so though we think a mirror like this would still work and scale, it's much more complicated and we think would make it much more challenging to commercialize. So instead, we're planning on using active stabilization of this interchange instability using shear flow or vortex stabilization in our plasmas. And so by doing this, we can keep the axisymmetric form factor and all the great commercial attributes while still having a stable plasma and having good enough confinement for a power plant. So the simple mirror is when you have two magnets on either end. That's the mirror that we're currently operating at the University of Wisconsin. That'll show in a few slides. But it's also the mirrors that a lot of the mirrors that have been designed in the past as well. However, when we do the best case scenarios for those mirrors and we scale up to Q, we see that the maximum gain of a simple mirror is around a Q of 1. And so you can use that to make a lot of neutrons, you can use that to make a lot of fusion power, but it's not quite high enough when you include all the other inefficiencies in the system to get to a net electric power output. So in order to get to that point of making a power plant, we're taking a simple mirror and we're stringing 3 different simple mirrors in series in the same machine. What we call this is a tandem mirror, where we have 2 simple mirrors running alongside the center cell, which is where most of the fusion is happening. So in this graphic, you see that these 2 simple mirrors on either side, we call these the end plugs. And basically what you're doing there is you're driving this with very intense external heating, with neutral beam injection, electron cyclotron heating, and you're building up that electric potential to a higher value than it is naturally in the center cell. And so by doing that, the ions that would be leaving out the loss cones of the center cell would end up getting reflected back into the center cell by that now higher positive potential on the outside. So this allows us to enhance the confinement of the mirror system even more, so you get a factor of 10x improvement in tau at the same ion energy. What that means is that a maximum gain of one system turns into a maximum gain of 5, 10, 15, or even 20 plus. And so that's high enough to make a fusion power plant. So for Realta, the product we're working towards is a tandem mirror, which is 3 simple mirrors linked in series. And that's what we call the hammer class of devices. So going more into our why now, why are we doing mirrors? These are not new ideas in the sense of the mirror was one of the original fusion concepts, along with the stellarator and also the tokamak. But there's been a series of big advancements in mirror and technology physics that's really allowed us to reconsider these in a serious way for commercialization. So one of those is the HTS magnets that are really being pioneered by Commonwealth Fusion Systems for fusion use. And these allow you to run a 2x the field possible with LTS technology at much higher temperatures as well, which reduces your cryoplant needs. This is a game changer, not just for mirrors, but all of magnetic confinement fusion that uses external magnets. And you can think of this because that the fusion power density scales as beta squared, which is the normalized plasma pressure, times b to the 4th power. So if you double the magnetic field strength, you go up 16x in the fusion power density. That means you need a lot less plasma in order to make a lot of power, much more compact, commercially scalable machines. The other big advancement was really pushed internationally in Russia and also in Japan using vortex stabilization for suppressing interchange in axisymmetric mirrors. And so this really was looked at first outside of the US, and we're using this biasing scheme on WAM to drive these sheared flows to stabilize, and we're seeing this working quite effectively. What this allows you to do is to stabilize those interchange modes we were talking about before, but maintaining the axisymmetric form factor, which also gives you access to high mirror ratio. So all of these synergistic effects, a better performing product, more simple and better to commercialize, full stop. All of this pioneering advanced stabilization schemes allows that to happen. The last part are these advanced heating systems, so modern neutral beam injection, ECH and ICRH systems. We're using this cocktail of different approaches to heat the plasma that we think will result in the best performance. Currently, we're using neutral beam injection and ECH, and later this year on WAM, we'll be fielding the first ICRH system to kick up the ions to even higher energies in WAM. So I've been talking about WAM quite a bit. Here's a picture of the machine. It's not just pretty pictures. It is real hardware being built and operated right now. This is a baseball card of WAM that you're seeing on the right there. We're using 2 HTS magnets built by Commonwealth Fusion Systems. These have a maximum operating field of 17 Tesla. We're able to scan the mirror ratio by changing the strength of the magnetic coils in the middle there that are made of copper. And so by changing the currents in those coils, we can change the field strength and tune the mirror ratio accordingly. The length of the mirror between the two HTS magnets is around 2 meters, and the plasma radius at midplane is around 10 to 15 centimeters, again dependent on the mirror ratio that you're running at. We're using a neutral beam injection system for our primary heating system for the ion injection, and so this is 1 megawatts, 25 keV neutral beam energy. And then we're also using ECH, which is around up to about 600 kilowatts of heating into the electron channel at 110 gigahertz. And as I mentioned, we'll be adding this 1 megawatt RF system that will be targeting around 26 megahertz nominal frequency to kick up those ions. And so as a testament just to the modularity and the simplicity of this approach, we received these magnets from Commonwealth Fusion Systems on July 1st of 2024. And then within 14 days after that delivery date, we had first plasma and wham. So that includes the cool down and field ramp up time of those magnets. So this is just a testament to how simple these systems are and how quickly we can move at Realta to make great progress. Since then, we've been operating WHAM in both HTS mode with these high-temperature superconducting magnets, and we also have another set of copper magnets that we've been running with lately, which allows us to have a different mirror ratio regime of data that we can use to better validate our real twin simulations as well. So on that front, beyond the experimental physics aspects, we also have a state-of-the-art simulation suite called Real Twin, which we believe is one of the, if not the most sophisticated mirror simulation suite ever constructed. So within this ensemble of codes, we have a series of different buckets of physics. So one of those is equilibrium. So this is Pleiades. This is a MHD Gratcher-Frontal solver that's solving for Newton's second law, F equals ma equals 0, and solving for what the mirror equilibrium looks like. We then take that equilibrium and we plug it into our bounce average Fokker-Planck transport solver called CQL3D-M, which M is the mirror customized version of this. This is working very closely with our collaborators at Compex, and this is how we know what to expect in terms of performance, in terms of like an NT tau perspective. Then the question is, you have this equilibrium, you have these transport properties, does that equilibrium stay put? And that's where plasma stability comes into play. So we have an ensemble of different codes, both for the MHD side of the house. So we're using Nimrod and MUG, which are extended MHD solvers, to look at more of that fluid-like instability, like the interchange modes and the ballooning modes. And then we're also using some kinetic modes, like VPEC, to look at different kinetic modes of interest, like the drift cyclotron loss cone instability, and also the alpha ion cyclotron instability. Both of these suites of codes are used to really nail down what are the stability properties of our mirrored plasmas. The last buckets here are really focused on the neutral beam deposition, which is one of our main heating systems, and then also the RF wave coupling. So this is for ECH and also ICRH that we'll be bringing online soon. Those are also through collaborations with Compex and MIT using the full wave aorsa code. So the point of Real Twin is to really take engineering inputs in terms of the plasma heating specifications, plasma stability actuators that we're using, like in-ring biasing, and the magnetic coil currents and locations, and then run it through this code suite to then generate the physics output of interest, such as the power, the fusion power output, the power gain of the system, the Q, the triple product, the confinement times, and also generating the synthetic diagnostic signals that we can then directly compare to the experimental measurements on WHAM to make sure they're in good agreement. This is really the process of validation that is so important for making sure that you can trust your codes to then use to design future devices. So to finish up here, I'll give you a good taste of the why and what we're doing now. Let's discuss now the path forward. And so we're continuing operating WHAM, and we're pushing that into the advanced performance regime as we speak. In parallel to that, we're designing our next stage device. We'll be de-risking a lot of subsystems as part of an AMBL project focused on getting the neutral beams ready and the magnets ready and other feedback control systems ready, along with the facility site itself for the Hammer machine, which is our next large-scale fusion device we'll be building at Realta. This Hammer DD device is a full tandem mirror at commercial scale that will be endeavoring to generate NT tau triple products in the center cell in excess of 10 to the 21 keV seconds per cubic meter with an ion energy above 20 keV. For the discerning reader, if you put that on the triple product plot, that is Q equals 1 net equivalent conditions in DD, and that is the goal we are setting for hammer DD. The reason why it's DD is that we're keeping with deuterium for the next stage machine to reduce the capex of not having to deal with tritium, but also to avoid having to build larger magnets and other systems in order to tolerate a higher neutron flux. We can really take out all the remaining physics risk of the mirror in this device, show that it scales, and then we'll be in a position to then switch to DT machines, which is what we're targeting for our first of a kind fusion power plants, with hammer DT targeting first deployments in the early 2030s. So I've alluded to these attributes of the mirror, but I really want to drive this point home, is that the mirror is a uniquely modular system in the fusion landscape. You could think of the approach, the product, as really two SKUs. You have an in-cap unit and you have a central unit, and those in-cap units are largely fixed, independent of your power output of your system. And so if the customer comes up and says, I don't want 50 megawatts, I want 150 megawatts, we can drop in additional centrocell modules in order to increase the power output of the machine while those in-cap units stay fixed. And so then we can also keep going, and we can scale that in parallel all the way up to gigawatt class. We think for a single unit, the sweet spot for these types of systems will be anywhere from around 100 megawatts up to about 500 megawatts per system, and we're targeting different lengths of the system to generate those different power outputs. But then if you want to go to gigawatt class, you build multiple units of those in parallel at a single site, and you can really get up to multi-gigawatt class no problem. And so when we think of where this fits in the landscape, we think the mirror is uniquely positioned to go small power outputs, large power outputs, and everywhere in between. And because of the modularity, we really can service customers at a competitive price point at really any of these power outputs in that power range. And so whether we want more central units to get up from 100 to 500 or more cylinders in parallel to get up to gigawatt class, we can do it all at Realta. Really appreciate your attention. Thanks for listening about the mirror. And if you're interested to learn more, please visit our website, realtafusion.com. Also, we're in Madison, Wisconsin. If you want to come visit us, we'd be happy to give you a tour. Thanks.
Thank you, Derek. We have one more presentation before our live panel. Next up, we're going to hear from Carolyn Sorrick, founder and CEO from EMP Technologies, Mason Wolak, VP of Capacitor Development at Peak, and Shaun Walsh, CMO at Peak.
Hi, folks. This is Shaun Walsh. I'm the CMO at Peak Nano. And I am probably the only person on this conversation that does not have a PhD, so I am not going to be talking about technology. However, I do want to talk about one of the core things, which is commercialization. And at this point in time, I think to say that the world needs fusion energy is an understatement. I don't care which prognosticator you talk to. We are now living in the age of electricity. And some of the easy benchmarks to look at here are, it used to be about 0.3 of a watt to do a search on Google. Now it's 3 watts. Multiply that times tens of billions of inquiries every day, and you start to see where the AI story comes in. If you believe our friends at JP Morgan, we'll be spending somewhere on the order of $5 trillion on AI infrastructure. A great deal of that is going to be power generation as well. A number of the hyperscalers are deeply invested in all of the members of this webcast. And we know that about $2 trillion is going to be spent on new utilities. So all of this boils down to one fundamental thing. The world needs more power, and they need it very cost effectively. And I think that's one of the other things that fusion energy brings to the table in a 24/7 dispatchable way that renewables don't today. So if we look at what's driving that, the obvious growth in power grid. And again, I'm not going to read everything that's on this slide, but if you look at what's happening inside power grids today, solid state transformers, solid state high frequency switching, and AI management are changing the way in which power grids operate, and that requires a different approach to energy, and fusion will be able to help deliver that. AI data centers continue to grow, and fusion energy is one of the solutions they're looking for in the future. Then we obviously have the different types of fusion energy that need their own energy to get started, the first queue, so to speak. And then EVs and charging, as we have seen with many of the world events right now, demand for that class of storage or that class of transportation continues to grow. So what does all that mean as we look forward? This is a report that Mike and the folks from Ignition Research have done. And if you look at the forecast today and you say fusion gets to about 20% of power generation over the next 30, 40 years to 2050, that means we need somewhere between 1,500 and 2,000 plants at 1 gigawatt each in order to make this work. And that growth curve is one of the biggest challenges for both the supply chain and the power infrastructure that would support that supply chain and these new fusion systems. So as we look at some of the next speakers in this section, we'll start to see where that comes into play. And most importantly, how can we drive the right price point? And a while back, Bob Mumgard published a blog that talked about major milestones for fusion. And one of the statements that stuck with me was fusion power must reach $50 per megawatt hour to be a price point that's competitive to win in the market. And I think that really is a good target for the industry. So here's a chart that came from Lazard. It was also published in Bloomberg. And if you look at the other sources of power that are out there, if fusion hits starting at 50 and even $100 per megawatt, it's going to be amongst the most cost-effective types of fusion there is. So that's the end of my prepared remarks. I'm going to hand it over to Carolyn and let her tell you how she's going to help make that cost target happen in the world.
Thanks, Shaun. I appreciate it. All right, before we jump into E&P technologies, I'd like to kind of take a step back and recognize the evolution of many fusion approaches that Shaun mentioned that we have today. All of these approaches we see, they vary in scientific reasoning, but as the industry starts to settle in, you're starting to see similar or repeat approach models emerge. And one that has a lot of backing and is picking up trend is impedance matched inertial confinement. So IMG architecture is really what I would consider a breakthrough innovation on the path to commercialization. From my perspective, it unlocks what I would consider an underestimated power within its design. And I'm not strictly talking about the actual performance power from the system. I'm talking about the power of simple and scalable operations that it holds. So many key advantages from this IMG approach include streamlined designs, which means less hardware, which typically means less complications, but it also has module-built systems that enhance its manufacturing and maintenance activities. So this shift from traditional single-shot research machines that you tend to see in typical pulsed power solutions to scalable modular power systems drives an entirely new challenge that we see today, which is demanding that we have repeatable, reliable hardware at scale. And that's precisely where E&P Technologies comes in. So my name is Caroline Sorrick. I'm the co-founder and CEO of E&P Technologies, where at our core, we design and manufacture advanced high voltage capacitors for extreme energy environments, just like fusion, other pulse power applications, and advanced power systems that can be found in defense and aerospace as well. So the company was founded to challenge what has historically been a very stagnant, overseas dominated field out of a direct firsthand experience working in the fusion system development industry. We recognized there was a major gap in the supply chain for high performance pulse power components. And we also saw that capacitor technology wasn't evolving at the pace required for these next generation systems. So our focus started to shift on rethinking how these components are not only designed, built, but how they're operated. So we do this through a series of cutting edge initiatives that we'll cover in upcoming slides today. So at ENP Technologies, again, we're not focused on just delivering hardware. In fact, we are working to innovate solutions that can meet the demands of these extreme applications. So our products evolve alongside our customer needs, keeping pace with cutting edge requirements of industries just like fusion. We're not just developing existing components, we're re-envisioning what capacitors can actually do, and we're pushing the boundaries of durability, performance, and reliability in these extreme environments by partnering with innovators like Peak Nano. So at ENP, innovation, it really is more than just a buzzword or a developmental concept. It's about how we transform the way we design, test, and manufacture capacitors. So we're doing this through a series of initiatives that really advance our products by building an AI-driven design platform to help speed up iteration, but also to integrate our customers' requirements from the start. This will allow us to build an all-inclusive solution based on final operating conditions and even suggest solutions down to the micro level, such as high-performance material mixtures like peak nanofilms. This will allow us to deliver more compact and the most high-performing products as possible. In fact, our products can also feature advanced embedded diagnostics and feedback technology that will be paired with an advanced AI software for real-time insights such as performance highlights, predictive maintenance alerts, and even troubleshooting support and suggestions. So this will allow you to know exactly how your capacitor is performing or trending to perform in your system. And on the manufacturing side, the way we're leaning into innovation is we're using advanced automation and predictable with repeatable processing to ensure that we're reshaping and reaching scaled production. We're also pairing this with a pod-based method to enable higher throughput and mass batching. To simply summarize as a whole, we're rethinking every step along the way to deliver faster, smarter, and more reliable solutions. But you might be asking, why does all this innovation matter? And I'll tell you specifically why it matters to fusion. Capacitors are mission critical to the majority of the fusion approaches that we're seeing today, particularly the one we mentioned earlier, such as inertial confinement, IMG. And we're talking about systems that are storing megajoules of energy and discharging within nanoseconds of precision. And we're doing that repeatably, reliably, and at massive scales. In fact, fusion at power plant levels, to me, isn't just a one-time scientific demonstration challenge. It's actually an operating challenge, which means components like capacitors must function seamlessly on an ongoing, stress-filled basis, and manufacturing must also scale to meet those demands. And this is the exact problem that ENP exists to solve today. So lastly, I want to highlight three meaningful elements of how we evolve with the companies that we work with. Some of these are our cultural tenets, such as ENP. Speed is not just a goal for us. It's how we truly lean into our operating conditions and our culture. We take innovation seriously and we move fast by combining novel technologies up front into our baseline products rather than waiting for the industry to catch up. Next, we prioritize use cases. So every solution is analyzed and designed around demanding power requirements from first conversation to final output of the product, which then leads us to delivering actual hardware. We believe truly in the art of building early and the power of the prototype, which will allow us to iterate from real world data and validation through testing campaigns, not just through endless design concept cycles or even software modeling. So there is truly no better way to optimize a solution than to allow the hardware to communicate its needs to you directly. So with that, thanks for allowing us to share a little bit about what we're building here at ENP. I'm now going to hand it off to Mason to explain how our partnership with Peak Nano enhances our products.
Thanks, Caroline. Very exciting to hear about all of your approach towards an advanced capacitor solution. So one of the things that got us excited about working with ENP Tech was the fact that capacitors are kind of a stale technology right now. For basically the last 50 years, you've had companies basically using polypropylene as their base material. And I think what excites us about working with EMP Tech is the fact that you have that innovative background and looking to kind of push the boundaries of what a capacitor is and how a capacitor performs. And we do likewise at the film level. So my name is Mason Wolak. I'm the VP of Capacitor Development here at Peak Nano. I'm going to walk you through our approaches to enable a material system that we can get out to cap manufacturers that gives advanced performance in very challenging applications such as fusion. So the basis of everything that we do is nano layering. So what we do is we take two different polymers, we melt them together, and then we stack and fold them into a multi-layer structure. So what this allows is for us to target different polymers with different dielectric, mechanical, and thermal properties, and then put those two materials into a layer structure with a very precise definition of the composition of the two materials and the number of layers. And that unlocks a new property set in capacitor film that is unlike any property set of a off-the-shelf type of material. Peak Nano has two commercial solutions towards fusion, and these are Nanoplex HDC film, which is our high dielectric constant film. This film is getting traction in the IMG type of pulse power systems for inertial fusion. This material is designed specifically to have very high dielectric constant, which means that you can store more energy in the same unit of volume, which is very critical when it comes to building these IMG pulse power modules, because the smaller that you can make the capacitor, the more capacitors you can fit per module, which means you can shrink down the total size of the module and decrease the cost of construction for the module, right? Because there's a lot of cabling, because you're delivering megajoules of energy, so you need very expensive thick cabling. So decreasing the size of the module offsets the cost of construction. Our other material is Nanoplex LDF, and this material is designed specifically for high temperature operation and to mimic the dielectric characteristics of polypropylene, which is a material that most cap manufacturers are used to using with and designing with. So what we've done is we've taken the operational temperature of polypropylene and extended it out to about 135 degrees C to unlock higher performance in capacitors that require polypropylene-like performance as a baseline. So I'm going to start a little bit with the HDC film. As I mentioned before, we have two commercial offerings, our 3125 and our 4125. The dielectric constant of these two materials are 3.7 and 4.8 respectively. So you're more than double the dielectric constant of polypropylene. The advantage of the high dielectric constant coupled with the very high breakdown strength of our material is that you can store more energy per unit volume. So there are always trade-offs in designing the layer structure between the dielectric constant you can achieve and the dissipation factor that you get for the material. So this gives us a full design space that we can work in. So the nice thing about the two commercial offerings within HDC is that the source materials are exactly the same. But as we change the internal layer structure, we change the bulk property of the film. Next slide, please. To give you an idea of how powerful this is, this slide basically shows more than 10 different formulations that we've developed with HDC. So on the right-hand side, you see some internal layer structures that are imaged with scanning electron microscopy. So you can see that the top and the bottom layer structure here have completely different compositions. The one on the top has very thick layers of our high dielectric constant material, which is the white layers. And the one on the bottom has very thin layers of that high dielectric constant material. And that allows us to move the dielectric constant and the charge storage capability of the capacitor film around as a function of the composition. And from a fabrication standpoint, the only difficulty here is we just kind of change some knobs in terms of running our melt, and that changes the composition. So we do this inline. We don't have to take our system down, do any clean outs or anything like that. We can run this in real time and change from one composition to the other and generate completely different property sets of the capacitor film that we're making. So as we work with fusion companies, we start to understand what the rep rates of their capacitors and their IMG system is designed towards. That allows us to then match, well, how much dissipation factor can you tolerate? If you're at a low rep rate and you can tolerate high dissipation factor, we can deliver a solution with a very, very high dielectric constant that would have 3 to 4 or 5 times the energy density of standard polypropylene capacitors. But if you need a trade-off between rep rate and energy density, we can go in and design a material that's specific for your system. Thank you. I'm going to switch gears here for a second and talk about Nanoplex LDF's film. This is designed for essentially a completely different type of application space, but it will definitely have use in fusion systems. For example, if in magnetic fusion where you're operating at higher frequency, you're generating a lot more heat in your capacitor. So your capacitor film needs to stand up to that heat without failure. So the LDF formulation is essentially polypropylene with thin layers of a thermal stabilizing polymer. And what these thin layers of polymer that are thermal stabilizing do is build out dimensional stability in the polypropylene. So the major aging mechanism for polypropylene is shrinkage over time. So as polypropylene is exposed to high temperature and high voltage, it will actually shrink and degrade in performance. So our approach here is to thermally stabilize the polypropylene such that it does not shrink at high voltage and high temperature. And if you look at this video here, Jalen, can you kick this off? You'll actually see the polypropylene winding shrinks, whereas the LDF winding does not. So this is a stop motion video, 150 degrees C for 1.5 hours. So what this does is unlock the ability to use Nanoplex LDF and high frequency fusion applications to extend out device lifetime and cut system maintenance costs. Next slide, please. So we're working with a variety of different capacitor manufacturers to develop this material into commercial solutions specifically for fusion. And we've been able to characterize the film as outperforming polypropylene in terms of high breakdown strength at high temperature, decreased loss, and more stable dissipation out to 160 degrees C, and an improvement in the stability of the capacitance as a function of temperature. So in the graphics shown here, the LDF data is in green, and you can see a distinct advantage over polypropylene in all three of these application or operational use cases. So these are two materials that we've been developing at Peak. We have multiple new materials that are under development. So we're targeting high energy density, high temperature performance, and the ability to shrink down the footprint of the capacitors that are made with our film. And the partnerships that we have with companies like EMP allow us to drive our high performance film into a high performance capacitor that's designed specifically for fusion applications. So I'm going to bring all of this around full circle here and leave you with the slide that Shaun started with, talking about the technology demands that are really driving the need for high performance capacitors. And although fusion is a huge portion of this, there's obviously other applications outside of fusion that require this level of high performance capacitor. Thanks.
So I have a list of questions, and we'll kind of give you guys some time, about 10 minutes to answer each question between the group, and then we'll go on from there. So the first question is: since the webinar is about progress towards achieving commercial fusion, do you think in general that as an industry are on target, ahead of target, or behind target against a 2035-ish, and I say it because obviously there's some play here, but it's that sort of target. Do you want to start us out, Mike, and kind of go with you?
Yeah, for me, yeah. Thanks very much. And again, thanks for organizing this panel. It's a real pleasure to be here. I mean, I think the future is difficult to predict, as they say. But we are in a fundamentally different world now than we were just a few years ago. Achieving ignition on the NIF, getting to that point of energy gain, getting the 60-year exploration of the physics of can we get fusion to be harnessed here on Earth. That threshold was passed, just a few years ago now. And so at least from our perspective at Inertia, how we project forwards is no longer about trying to predict a physics exploration. It's moved into a different domain, a domain of can we harness the technologies and can we build up the supply chains to be able to replicate that fusion ignition, that fusion gain event again and again and again. A much more predictable world than, speaking as a plasma physicist, much more predictable than exploring into the unknown vistas of physics. And so, when we look at our particular plan, looking forward at that prototyping phase, the scale up of the supply chain, the construction of the plant and so forth, it is a decade kind of timescale, maybe in our particular plan towards the end of the 2030s, but in a mode that is definable, quantifiable risk, and you can assess the likelihood of being able to achieve it by analogy to many, many other areas of technology. So at least from our point of view, yes, we're in a more predictable world. Let's hope other approaches can get into this mode as well. I'm pretty excited. The reason I came back into this field after spending 10 years in a different world was because we're now in this fundamentally new era.
Are we just to jump in?
Looks like Mike's
Sorry
trying to
about
unmute.
that. The mute button was hit on me. Derek, what are your thoughts on the matter? And then we'll jump
Sure.
early.
So first off, want to clarify the question. So 25 specifically to deliver what is the question?
Commercial fusion power on the grid.
Okay. So I would say, the industry as a whole is on track to getting to, a first of a kind net power producing system. I would say there's a lot of engineering milestones that need to be demonstrated, depending on the concept, also physics milestones that need to be demonstrated as well. I would say the other big assumption is that there's a sufficient amount of capital to advance all of these concepts at the level required to get to that point. But from I would say an industry level perspective, I think we have a lot of momentum behind us. I think we are starting to focus on the right problem. I think everyone meaning the industry or the field at large, has been really focused on Q equals 1, and they should be. That is or at least net gain enough, whatever your system is, to get net electric. But after Q equals 1 is what I'm most interested in, because that's when I think the rubber meets the road as far as what actually is cost effective enough to deploy and compete. And that's where I think you'll see a lot of different approaches to fusion that are serving different market segments. And just because one product works in one area doesn't mean it applies everywhere. So I'm really excited to enter that mode. I think we'll get into that mode in the next 5 to 10 years, and we'll see who makes the best product in the end.
How about you, David? What are your thoughts on this matter?
So short answer is, yeah, we're on track. We're on track on a very aggressive schedule. There's no reason to set unaggressive schedules. I'm a believer in aggressive schedules. I've been involved in a lot of projects, and you have to work to meet schedules, and we're going to do that. We're going to do everything in our power to make that happen. I think there's been, already Derek just mentioned, we have to raise capital, we have to solve engineering problems, we have to generate power. And those are big lifts, but we're on track to do that.
And Charlie, what do you think there?
Yeah, look, I agree with everything that everyone said. To David's point, I don't think it benefits any of us to have targets and timelines that are not ambitious. I think to attract the capital that we need to demonstrate that whilst ambitious, they are still tangible and credible. And that involves both technical milestones and, as we all know, the supply chain actually maturing at a similar pace that can support deployment. But I think, depending on the technologies, there is a very real chance, and our own timeline and our announcement yesterday with the partnership in the UK is, with a view to putting electrons on the grid by 2034, 35. And I think the interesting thing to the capital point is, I think just in the last couple of years, you've seen a real inflection in terms of the attitude of investors with, I would say, the majority now accepting that fusion will happen, but it's a question of when, as opposed to even 5 years ago, you had a lot of people who were still very cynical as to whether or not fusion would ever be a practical reality. So I think you've crossed that threshold. Now I think it will be, once people have confidence that there is a commercially viable and practical fusion power plant solution, I think, frankly, the amount of capital you will see flood into the space will be somewhat unprecedented. So I do believe once the preponderance of sort of public opinion is fusion's happening and it's happening now, the capital will not be the impediment.
That's good to hear, because certainly you can't get it done without money. And
No, you
as
need a
much
lot of
money
money.
as you. Go
You
ahead.
need a lot of money, but there's a lot of money going into other things that I think will be diverted to fusion once fusion demonstrates its viability.
Shaun, Carolyn, and Mason, from a supply chain standpoint, what are your guys' thoughts?
So I'll take a cue from what we're seeing in terms of demand. If I look at the 10-year shot clock and how many people were asking for samples of material, it would have been less than a handful. A year later, it is significantly more than a handful. So while I can't speak to the engineering progress of each of the various designs, I can tell you the activity and the real work of building machines certainly appears to be moving forward.
Yeah, and I'll jump in here. As a hardware supplier ourselves, one thing that I think is pretty neat that you've seen throughout this entire webcast, and if you follow any Fusion developer on LinkedIn, is there's actual visuals and demonstrations via hardware. I mean, that is so cool. I think even just from last year, but really within the last 3 to 5 years, you've seen that explode. And I mentioned in our presentation, we truly lean into the power of the prototype. Allowing the hardware to provide that feedback real time will help cut down on design iterations and cycle churns. But now that you compare that with AI and digital twins, you're going to see an evolution of the scientific discoveries and milestones speed up very quickly. And as everyone mentioned too, private capital is going to compress those timelines dramatically. What used to take scientific milestones to then drive decisions, to then wait on the government, is totally removed. And you're going to get an expedited delivery of those results. I think the engineering challenges are still real, but the urgency and the cultural investment behind fusion has totally drastically changed anything I've ever seen before. So I think we're cautiously optimistic, but 2035 is not that far away. And I don't think it's no longer a fantasy anymore either.
It's good to hear.
I'd also like to jump in. I want to follow up on what Charlie said on really firming up the supply chains. This is really important here. And I think that there are a lot of people who don't really understand kind of the scope of what it's going to take to enable that, the kickoff of the fusion reaction for these reactors at scale. We were just in a cap manufacturer facility recently, and the engineer there said that they had been approached by a fusion company, and here's the requirements for the capacitors. And we walked through an 80,000 square foot facility, and the engineer there said, well, in order to hit this target, we actually have to build another facility just like this. So firming up the supply chain and getting ahead of that and understanding what needs to be done at scale. If you're looking at deployment of hundreds or thousands of these reactors, and then you start looking at, well, what does that mean from a supply chain standpoint? And you need to start anticipating that now and planning for that now.
That's good to hear. I think I even know which cap manufacturer that was. So, yeah, there's a lot of interest for sure. So, second question: in our recent series we call the Fusion Decathlon, we talked about 10 different events, so to speak, that were had to be solved to get fusion off the ground. If you had to pick a single greatest challenge, and you don't have to pick the ones we had, you can pick whatever you want, but if you had to pick the single greatest technical challenge or funding challenge or people challenge to achieve commercial fusion right now, what do you think it'd be? And Mike, we'll go ahead and start with you again.
Yeah, I'm going to cheat and talk about two things rather than one, if you don't mind, Mike. So I mean, there's no getting away from the fact that in general, crossing that physics barrier of how to get with any of these given systems, how to get the plasma to behave at scale, is of course the existential challenge, for all approaches. And we shouldn't minimize that. The history of fusion is not great in terms of being able to predict, will the next machine cross that barrier or not? So, being honest with ourselves about how hard that challenge is, it has still to be number one. Even in my own area, of having being able to ride on the wave of what happened at the National Ignition Facility, how we scale that up, is something that should be front and center for all of us. That said, at least from my perspective, the topic that was just mentioned by Mason and previously by Charlie, the scale up of the supply chain is foundationally important. Factors of hundreds to thousands scale up in volume, even for the first pilot plant for key components, whether they be semiconductor laser diodes or the manufacture, in our case, of these little fuel targets and so forth. We shouldn't minimize that. And so I would characterize the challenge in one word, and that word being confidence. Confidence in that supply chain to invest in that next plant or invest in the automation steps to get to that next plant. The NRE that takes, the diversion away from their existing boutique markets that takes should not be underestimated. And so the degree to which we can act in concert where we have common cause, whether that be in back-end fuel cycle technologies or front-end, high voltage power supply technologies, the degree to which as an industry we can act in concert to drive that confidence in the supply chain, that they're not betting the farm on one startup, or one particular mode of approach to fusion, but instead looking at the wave that's coming, I think as Caroline talked about earlier. And this is also where the US government can play a part in providing that backing, that confidence, that strategic overlay in terms of how we move the community at large.
Excellent. Derek, what are your thoughts on that?
Yeah, so I tend to focus more on the kind of the end goal of where we want to get to. And I would say one of the biggest challenges I see is, back on the capital, access to capital front. I think like for any fusion concept to really get across the line to a first of a kind, I mean, you're talking about a 10 to the 8 to 10 to the $9 proposition. And so there's a question of, how many of those types of companies will the market support? And there's an open question there of if there's going to be access to non-dilutive capital to augment that as well. But I do think like getting to a first of a kind is going to be done by the private sector, because it's really the only thing that can really scale and go fast, and also is the best type of entity to drive down the cost of fusion. And so then my other part is on the economics of fusion long term. I think, beyond Q equals 1, that's really one of the focus areas at Realta is like, how do you make this cheap? And what I mean by that is like we have a very competitive marketplace. You have natural gas, there's solar and storage, there's advanced geothermal. And in the end of the day, the watts coming out of the wall are the same watts. It just depends on where the source is changing. And so I think what we found is like, in the end, people want cheap power. No one wants to pay a penalty for being clean. And we have some competition. So in the end of the day, like fusion needs to be cost effective or it's not going to matter, in my opinion. And what that means to me is like we need to get under $50 a megawatt hour with a line of sight towards like 30 or less dollars per megawatt hour. That's challenging. I think there's also a challenge too because of the difference between LCOE projections and the total capex to get to the first of a kind. That latter part seems to be the main hurdle for us right now is the capex to get to the first of a kind. So we can get to that nth of a kind cost target. So there's a lot fewer people on Earth that are willing to write $10 billion checks than $1 billion checks. And so
the more cost we can take out of these R&D devices, the better we can get to the first of a kind.
David, what are your thoughts on that?
So when I first started thinking about this question, you actually asked, what's the biggest challenge? But then you said people. It could be people. It could be technology. It could be supply chain. Like Derek just said, it could be techno-economics. It could be just capital raise. We have challenges in all those areas, and what you view as the biggest one might depend on where you stand and the way you think. I'm a fusion researcher. I've been that all my life. I tend to think in terms of fusion technical challenges, but now that I've been in business for a couple of years, I start to appreciate the difficulties of techno-economics and raising funds. We've been recruiting people very actively. People exist that have the skills we need, but not enough to run an industry that builds thousands of power plants. And if you look at supply chain, most of the things we're planning to use, with a few exceptions, exist. And people make them, but they don't make them at scale, right? And each of these problems is pretty. So I think if you're a person who thinks about supply chain, you're probably going to say the biggest challenge is scaling up all of these products that we make, at low levels now, like cryogenic systems. You can buy a cryogenic system off the shelf, but it's pretty expensive and it's 6 months delivery. And I want one that's 10 times bigger, and I want 1,000 of them. It's a very daunting challenge for a person doing manufacturing. We've made fusion. NIF made fusion. Tokamaks have made fusion. But we want to do it for like a year. So I tend to think of that as a big challenge because that's who I am. I work on making fusion. That's a lot of heat and a lot of neutrons. And but we also talk about we've specified an alloy that we think would be ideal for the first wall of our device. And they make it. You can buy it. You can buy tens of grams. And I want tens of tons for thousands of devices. And that's just a big develop. I mean, how do I make that cheaply? I don't want it to be one of the most expensive materials on Earth, right? I'm buying tens of thousands of tons. So, I'll tell you who I am. I'm a fusion researcher, and I tend to see the technical issues with fusion, and really it's that heat. We got to deal with those neutrons, and we got to deal with that heat. But of course, that's the goal, and we will do that. And we have lots of ideas on how to achieve those. So
very good.
I didn't pick one there, you noticed.
That's all right. Charlie, maybe as the finance guy, you have a slightly different view. What were you?
Yeah, ironically, I'll probably take, I won't get out of my skis here because, as you point out, I'm the finance guy. From the finance side of things, as I say, I think if we keep hitting our milestones, and the promise of fusion is so existential to so many things that I think the motivation for the dollars to follow and the supply chains to scale and everything else, there will just be a critical tipping point where once people realize the reality of this, particularly as you continue to see baseload power consumption increase in most markets, with probably the exception of areas of Europe, I think the motivation will be there. People will be highly motivated, and what you will see is a divergence of capital from other areas. I think when we think about it from a technical side of things, one of the typical questions you get is about, well, certainly for us with a DT reaction, is tritium. How do you breed the tritium? And of course, no one has, whilst there are ways to do it, no one has demonstrated how to do that effectively in the context of a fusion power plant. So I think that is one of the biggest technical challenges that people still want to be convinced you have a solution for. I think, to David's point, I think the interesting thing is there are existing materials and existing technologies that can be adapted in unique ways to achieve what we need them to achieve. And I think that's critical in terms of, again, instilling the confidence that the solutions that we're working on are actually tangible and there's a credible timeline. And, the ceramic pebble bed technology that we're looking at is one that is used in other contexts today, but will be adapted for these purposes. But I do think there is a demonstrable path to solving for tritium breeding as a prime example. And I think there are credible paths with a number of these technologies. And again, to the point whilst there are very unique approaches to fusion, as we all know, there's a lot of commonality in areas of the supply chain and the technologies that need to develop and scale. So equally, you're not necessarily asking, I think to Mike's point, you're not necessarily asking someone to take a risk on, just one technology or one solution. If that one doesn't work, then what on earth did I spend my time and money on? So I think that's one of the things that always appealed to me and attracted me to fusion was the collaborative mindset. Even though people are taking different approaches, there's still a very large degree of the rising tide floats all boats here. So I think being able to continue to collaborate and encourage supply chain partners to develop these solutions because there are multiple avenues for success. And frankly, a market which is so large, that there will be multiple winners, there will be multiple technologies. I think to Derek's point, there'll be different applications for different technologies, and I think that there's an opportunity for a lot of people to win. That being said, there's going to be a period of consolidation in the next few years because you can't continue to support 60 plus private fusion companies, although a number of those will focus, I think, on niche capabilities for which they're market leaders. So that consolidation, I think, is going to be a challenge, but also an opportunity.
Really, I agree with you 100% there. Shaun, Carol, and Mason, hopefully you'd say that the supply chain would be one of the big issues, but I'll let you guys answer that yourselves.
Yeah, I think that when you consider the scope of what we're talking about here, you say, Mike, I think your report starts at 1,500, maybe as high as 2,000 1 gigawatt systems. I remember a quote from Randy Curry before he left Sandia, and he said, "We're going to need football fields of capacitors." And you think about the videos that a number of folks have released in terms of the size of the power systems that are going into this. The film lines that make the capacitor film that go into the capacitors that everyone in this industry use are 450 feet long and 90 feet wide. They cost $35 million to buy, 50 million to deploy. They produce 10 million pounds of film a year. Many of the folks that we have spoken to will probably use that or more on an annual basis. So to support 2,000 fusion systems, you're probably going to need 1,000 of those machines running 24/7 for the rest of the time that fusion energy exists. And we're just one component. So yeah,
It's more like a racetrack than a football field almost.
yeah, there's and we're not alone. I mean, we're just one component. So I think that getting the supply chain moving in the right direction is certainly going to be one of those things. And the big problem is that, to Charlie's point, there's 40, 50, 60 one-of-a-kind designs. And we're going to get to a point where as an industry we need to scale, and you can't do that with that many different versions of it. And then the last thing I'll throw out there, I'm going to pick two, is I think it was Mike who said I'm going to pick two. The other is you got to build all this. One of the things that has always surprised me is, for all the fusion plants I've visited, how big the machine shops are. Electricians, welders, machinists. If you look at history, for every PhD we have working on this, probably going to need 10 or 20 engineers and 40 or 50 highly skilled tradespeople to make these machines go from concept to deployable power systems. So I think the other piece to this is going to be training up the rest of the workforce to go with it.
That's good.
Yeah,
Thanks for stealing.
go
Sorry.
ahead, Mason.
No, I was just going to say thanks for stealing my answer there, Shaun. I was going to basically talk about really the need to build the talent base here, training the fusion engineers, training the technicians, and building up that base of people that speak the language of fusion. This is not an insignificant challenge right now, particularly when you look at this from the standpoint of, deployment 5, 10, 15, 20-year time horizons. You're talking about people who are young right now, and you want to bring in that excitement. And this goes back to what Charlie was saying about getting the public on your side. there are probably engineers and PhDs right now that are in high school that are going to be impacting deployment of these systems. So I think that's a serious challenge, especially in the current environment where we're defunding basic research and things like that. We need to figure out the ways to reinvigorate the workforce and get people beyond the people that are on this call excited about fusion.
Yeah, and just to summarize and throw in maybe one last perspective, if I'm looking internally at ENP technologies, some of the buzzwords of repeatability and scale can be somewhat daunting. So it leads to a challenge of automation. So how do you automate production processes to reach scale? So when it comes to an actual tactical plan, are you ready to pull the trigger and execute on the high quantities coming through? To deliver reliable and repeatable products. So you don't have variances and any sort of outcomes, and you're ready to plug and play for the high demand. So I think, just kind of summarizing from what I'm hearing, repeatability at scale on every front, whether that's workforce, whether that's your production process, and really the scale of capital to support all of that infrastructure that's required.
Yeah, it's definitely an issue. And the people side of it, as one of the big surprises I got when I entered this discussion, is that how many people said people are a big issue. It's really surprising. Speaking of that, if you're speaking to President Trump and Secretary of Energy Chris Wright right now, what would you say would be the most important thing they could do to help increase the chances of achieving nuclear fusion? We'll go ahead with you again, Mike.
Yeah, I would say two things. I would say, first of all, the US government, both the executive branch and Congress, should be incredibly proud that they are leading the world in fusion. From the billions of dollars that have been invested in the NIF and in tokamak systems and so forth, and the only country in the world that has got to net energy gain, is directly as a result of the Department of Energy and generations of activity that has got to that point. So there should be real pride that we're out front, and we should try to keep there. And then what can be done at that federal level to really maximize progress, I think, is to be able to capitalize on that long-standing investment. There are capabilities in the DOE complex that simply cannot be replicated at any reasonable time or cost by any of us, whether they be baseline codes, whether they be very large facilities like the NIF, whether it be the workforce with incredible talents in the different labs. And so find a way to allow us, the private companies, to better access that capability without having to go through mounds of bureaucracy, lab by lab by lab, project by project by project, that can add months and years to a program. Expedite our ability, both as a community and as individual companies, to access those billions of dollars and decades of capability development. That will provide an edge that nobody else in the world has. There's nothing like the DOE system anywhere in the world. And so allow us to access it, allow us to leverage it, allow us to drive those public-private partnerships at a level that is much more effective than we see today. There's good green shoots of activity that have been appearing over the past couple of years, but it's nowhere near what it should be. I think with some executive action, they could make a huge difference.
Derek, what do you think about this one? What would you say to them?
Yeah, so I would say in the first bucket, so full disclosure, Realta is a member of the milestone-based public-private partnership program with DOE. I agree that should be funded at a higher level, and not just for us, but for all of the membership milestone companies and any newcomers to that program as well. I do believe, modeled after the COTS program, that kind of led to the rise of SpaceX and others. That is really one of the best ways for the taxpayer to get the best bang for their buck in paying for success, and then having the risk on the developers to raise the capital in advance. And I think that's a more fair way to actually do technology development when the government is involved at all. I would say the other element too is, we had a lot of great regulatory motion with the NRC, issuing law that fusion would be regulated under Part 30 which is a much more favorable treatment than 50 or 52 that applies for fission. And I would say, as another step beyond that is starting to think about where we might site these new first of a kind facilities, and if there's existing infrastructure at national labs or other federal lands that could reduce the capital costs required to get to a first of a kind demonstration, I think that's something that could be very helpful. I think the main risk to that is the lot of red tape and the bureaucracy that often comes with that national infrastructure. So if there's a way that we can be lean, mean, fast-moving machines while also making use of that public infrastructure that already exists, that would be fantastic. And I think that's something that the administration could really uh, help with, and really in the theme of reindustrializing America and getting more jobs right here at home.
Excellent. David, what are your thoughts?
So I want to thank Derek for using up about 3/4 of my response, and good job. We are also a milestone company. I actually had the pleasure of meeting Secretary Wright on a visit to Princeton one time, and the only thing I would add to what Derek said is I would remind them that other nations, both our allies and our competitors, are really investing into this space very heavily. In particular, China is outspending us in terms of developing new facilities. I would say about 10 to 1 right now. It depends on how you count that, because the way they count money is different than the way we do. But that if we're going to maintain our lead, which I think was rightly pointed out we have, we really need to do something to make sure that remains in place. I would also say, look, America has the most vibrant private sector as well, right? We have a venture capital engine that really drives innovation in this country, and it's unparalleled. So the combination of the U.S. government backing us through programs like the Milestone program, which, by the way, is at a funding level which doesn't really, trigger any events. That could be really powerful. If you look at the history of public-private partnerships in the United States, the Apollo program, the development of nuclear power, aerospace, the things that we do where and those were all public-private partnerships. We're very, very clear there. Those were industry-led, government-supported activities, and they were, the development of nuclear power is actually very efficiently run, and we should reproduce that and make the U.S. remain the center of this kind of activity.
Charlie.
Yeah, I think a lot of good points made by my colleagues there. I think, generally speaking, again, we too are a member of the Milestone program. We too are frustrated by the lack of appropriation of funding through that program, because I think the program's been set up in a very thoughtful and constructive way. I think from ours, going back to a comment that Derek made, at the end of the day, the adoption of fusion is to some degree going to live or die on, can we actually demonstrate that this is a economically viable solution, i.e. can we hit that $50 MWH LCOE or lower? I think for first of a kind plants, we all recognize we're not going to get there. I think anything that the government can do to support effectively either the capital cost and or as a result the megawatt hour cost for those first of a kind plants is going to be really, really important, because getting those plants built is the only way we're going to get down the cost curve, which I do think the regulatory regime under Part 30 is great, particularly because it allows us to have we don't have the quality assurance and other constraints and the regulatory burden which afflicts fission and means that that's never really going to get down to a truly competitive cost level, even with SMR technologies. I think fusion has a significant advantage there, but to take advantage of that, we need to get these first of a kind projects built. And as everyone's pointed out, people are less and less willing to pay significant green premiums for this kind of thing. So I think where the government can step in, we'll be supporting both the capital costs and that initial LCOE for some of those first of a kind contracts, whether that's, first loss risks backstops for the the capital providers, or the UK has a contract for difference kind of concept, which has been very effective over there. So a similar concept here where we can effectively underpin power purchase agreements for first of a kind projects, I think will be very important.
Excellent. Yeah, that's a really good point. Shaun, Carolyn, Mason, from a supply chain standpoint, where are things that the government could do specifically? Secretary Wright and/or President Trump to help you guys out.
I'm going to let Carolyn and Mason tackle this one first.
That sounds great. I think, cliche answer, but fund the supply chain, not just the science. In my opinion, commercial fusion will live or die on whether or not there's a robust domestic industrial supply chain to support it. And right now, many of those critical components are made by a small number of suppliers, but you're seeing some come from overseas. And I think a targeted and clear investment strategy in qualifying and scaling domestic suppliers now would dramatically reduce that risk across each fusion program in America kind of simultaneously if you were to kind of open and bring back manufacturing onshore for these components.
Yeah, I think we haven't seen a whole lot of trickle down yet. I think most of the funding right now in fusion is really on the how do you make fusion work side of things. So you do have some support funding coming out of DOE, like the FIRE program, but it's very clear that there's got to be an ecosystem that builds up around the make fusion work to how do you turn this into building plants and building them repeatedly. And that really comes down to, again, getting the public on your side, having the ability to kind of present to the administration that it's more than just making fusion work. It's making fusion work at scale over and over and over in multiple facilities.
Yeah, I think if you look at like nuclear fission, for example, the ecosystem there is very deep and large, and nobody tries to make everything there, or from plants to heat exchangers to everything. And there's no reason that fusion, shouldn't be the same way. So for I think what is probably our last question, I'm going to touch on.
Can I jump in before we go to the last question?
Yes, go ahead, Shaun.
So I have a very different set of things I would say to Trump. He and Secretary Wright are business people. They are leaving $5 trillion in revenue on the table. If, Mike, your predictions are right, and we're going to spend $1 trillion on plants, are they going to buy that from China or us? Globally, that's the big question. The supply chain going into that is another $1 trillion that they're going to spend on power grid. Think about all the power lines and substations and all the other stuff that's got to go into that. This improves everything else you want for national energy security. It's another $1 trillion in incremental AI revenue. AI is limited by one thing, how much power they can put on chips. $1 trillion in quantum computing. Think about how cold it's got to be to almost absolute zero to make quantum computing work. And then there's another $1 trillion that the government doesn't have to spend buying energy from Canada because you can get it domestically with fusion. What's more important to you? And I think one thing we've learned about this government is cash talks.
Well, I would just to build on that, I think to Shaun's point, someone described to me this is the most uniquely transactionally focused administration we've probably ever seen. And I think to that end, one of the things is traditionally we've always talked about non-dilutive funding from the government. I think one thing that could really encourage things here is actually say the government should be making direct investments in projects and companies, because why shouldn't the American taxpayers who are helping to fund these projects and these companies benefit ultimately from those that win? And some of these companies are going to be some of the most valuable companies on earth in due course, given the scale of what we're attempting to do. Why shouldn't the US taxpayer benefit from that in the form of direct holdings?
Agreed.
Well,
The alternative is we have to go to the private markets and raise the money privately, and those investors benefit. So why shouldn't the US taxpayer and the US government be the same?
and you look at the money the UK is putting into it, I mean, we should be the same, at least, if not greater. No offense to you, Mike. I know you're from the UK. So that kind of leads into a very obvious last question. How big is the challenge from China, and do you think there are as many opportunities to work against them as there are to work with them? I'll start with you again, Mike.
Yeah, the challenge is huge. We are, of course, in the US ahead of the game at the moment. But time and again, we've seen China take over. I'll maybe give one historical analogy that is very close to my own field. The technology that goes in all of our iPhones and so forth came out of a revolution called EUV lithography. That came out of the DOE National Lab System, the Berkeley Lab, Sandia, Livermore Lab, and so forth, a few decades ago. How do you get that very short wavelength light to be able to do the lithography of smaller and smaller chips? It was born in the US. But now, of course, the market leader, as we all know, is TSMC, over in Taiwan. And the market is captured, by ASML, based in the Netherlands. And to first order, no capability left here in the US, having been the market leader, the inventor of the technology. And so our challenge is twofold, isn't it? It's to stay ahead now by getting to these first fusion pilot plants in the ways that we've just described. I really like Shaun's articulation of how that can be built up from an economic point of view. But then putting the strategic building blocks to stay ahead. That's both supply chain resilience, it's IP capture. It takes federal government level strategic investment, as we've heard, but also the architecture of how you hold the community together to make sure that we don't win and then lose subsequently, as has happened in EUV and has happened in a number of other areas.
All right, let's go to Derek. What are your thoughts?
Yeah, I mean, I would say there's a lot of activity going on in China. That's always the case, it seems, in most technology areas. I would say, overall, Realta, we are paying attention to what's going on over there, but we're not letting it dominate what we're working on, and we're pretty heads down, just making our approach work. I do think we should pay attention to the supply chain, and in particular, where we're sourcing rare earths for YBCO, for magnets, and where we're, all of those different, raw resources, to make sure we don't end up in a situation where, suddenly exports are banned or something happens, and now we're out of luck for a major component. I mean, I will say, showing maybe a bit philosophy behind this, I'm very much a global market person, and I think that is where we should be going towards as a planet. I would like for everything to be trading back and forth freely. That's not the world that we live in right now, and it's kind of not the direction we're currently going in. But I do think we should strive on trying to get more working together with our allies and growing the list of allies there as much as we can. But I do think having domestic manufacturing capabilities is a good thing, and that's something we should consider. But I also don't think that we should be overly nationalistic, and we should work across the entire planet, because I think with something like fusion, it's going to take that scale in order to get it across the line.
David, I know you kind of even started this discussion out with your answer to the previous question. Do you have anything more you want to add to it?
So, I mean, I should start off by saying, I've collaborated with China for a very long time, up through about 10 years ago, when that activity tailed off. And we still have a treaty with China to do fusion research, and the difference is that the relationship isn't what it was, and international politics change more than once in my lifetime. That things have, who our friends are and who our allies are, has changed. So, I mean, right now, China is racing ahead to make fusion energy. They have a very serious need to power their country, just power it, period. Not, and they're deeply aware of the downsides of fossil fuels and, the geopolitics that we've seen recently. There's a lot going on in that space. So I think, when I was working with China, we really enjoyed that interaction. I'll be blunt with you. I kind of miss it. There's some really good people in their program, and I don't know if you know, but their tokamak's based on a design from Princeton. It's very, very specifically a copy of that design. So their ability to race ahead is part of they have a very strong national focus, right? They're very, we probably never will have that national level of focus, and we probably don't even want it. But I think the competition is real. That their program is world class. They're moving ahead. They're building tons of facilities at a rate we're not matching. So we may be in the lead at the moment, but the way they move, and I think the EUV lithography example is really probably the best one. We really need to maintain our lead in this space. So, and we better get going. So,
yeah, that's for sure. Charlie, I know being from Australia, you're certainly have a slightly different perspective on China.
I'm actually a Brit originally. I lived in Australia for a long time, but it's a British passport. So Mike and I are on the same page here. Yeah, look, I think the point is, as we've all emphasized, we currently have a lead and a technology advantage, but that is shrinking rapidly. And when China is deploying Manhattan Project style sort of mass force to try and win here, like that should be something which the US government in particular is highly focused on. The CHIPS Act was put in place for a reason, to try and win back what we had given away in our advantage from a semiconductor perspective. And I think that arguably the concern there is even more acute when it comes to fusion and energy security generally. So I think fate is still in our hands, and ultimately China will succeed, we will succeed. This is going to be $1 trillion a year plus market. You look at the AP1000 example. China now build AP1000 reactors faster and cheaper than anybody else. That doesn't mean that everyone's going out and buying AP1000 reactors from China. And I think the same will be true for fusion. But our currently demonstrable advantage is shrinking fast, and that should be another high level of motivation for the US government to really lean in here and maintain the advantage that we still hold.
I just want to jump in and say that my children are actually born in Oxford, so
there we go. Good.
I've passed on British heritage to my children.
Thank you.
Shaun, Carolyn, Mason, what are your thoughts on
that? I think that, again, this is one of those things, we've seen this movie before. Okay? This is a question of will. This is a question of choice. Pick your examples: batteries, chips, solar panels. There's a dozen examples of this. I hope that strategically, as a nation, we make a different choice this time. But, again, what you have to do at the end of the day, regardless of your opinions of China, whether it's good or bad or whatever, you have to respect their execution. And they have chosen to execute in this space. We have to decide if we want to execute with the same degree of vigor, energy, and commitment. And so far, unfortunately, history's not on our side. I hope we choose to behave differently going forward in this segment.
Yeah, 100%. Agree with you. Carol?
Yeah, I think on the note of collaboration, I would say that the window for a meaningful scientific collab is really quite narrowing. And then to David's point, the competitor, China being a competitor, is a serious threat, and it shouldn't be underestimated. And then just tying it with Shaun's point of the actual execution, where they have a clear advantage is the ability to build up and scale for supply chains. They've demonstrated it over and over again, where they're able to not only provide hardware, but they're able to do it at scale at a price point that is very appealing for not only, their own benefit, but globally. And I think that's something that we can actually use and learn from and see how much we can take into our model to help scale for this type of demand that's going to be blooming here shortly. But I think overall, the question is not to worry, it's to just continue to win.
Good point. All right, Mason, last panel thoughts.
Oh, geez. I don't know if I'm the right person to close out the thought here. No, I mean, I think everyone on the call understands the challenges related to competing with China. I want to give a little bit of perspective related to our small slice in this, which is on the capacitor film side. We're working with a company right now to specify a large scale line that gives us the capacity to make about, let's say, 10 million pounds of film a year. That same company that we're working with has taken 18 orders for lines from China. So China's already looking at this as looking at fusion development in a really kind of global perspective that the US is not looking at right now. They're looking at the securing the supply chain in advance. They're looking at, it's not only just building the reactors, but how do you go from that first of a kind to the 10th of the kind to the nth of the kind, as we heard earlier. And I think that longer term vision is the part that I don't know that the US and Europe is totally addressing right now. And that's a real serious challenge. And again, it comes down to I think that there needs to be more emphasis on that commercial side that Shaun was talking about, to sell the administration on the importance here, because it's going to come down to the right blend of public and private funding to pull this across the finish line.
I think that's a very good point. I mean, as Shaun has said, and he and I have worked together before in the IT world, and you see what China did there, and they did largely because we gave it to them and let them do it. And we have to make sure we don't do that again if we want to play in this space. Well, again, thank you very much, everybody. Thank you, Mike, Charlie, David, Derek, Mason, Carolyn, and Shaun.